This is video 7 in the grade 11 topic chapter on Newton's laws. And in video 7 we just continue our discussion about forces in equilibrium. In this video we're going to look at two methods. One is the component method of solving a problem, so taking forces and resolving those forces into their components. And the second method is using, if we've got three forces acting on an object and the net force is 0, then we can draw those three forces as a closed triangle. So the first question I want to look at is on page 36 of your notes. It's question 1 and it's exercise 1.9, and we're looking at this 40 kg mass over here that is being held in position. It's not moving, so it's at rest, and there's an applied force here to the right, a horizontal force of 231 newtons. There's a rope attaching that mass to the ceiling, and there must be a gravitational force acting on this mass. So you need to draw a free body diagram of all the forces acting on the 40 kg mass, then explain why you think that this mass is in equilibrium, and then the third part is to determine the tension in the rope. So pause the video, and once you've done that, come back and check your answer. Alright, so you've tried the question. You would have drawn a free body diagram that looks like that. We've got this horizontal force. Remember, we use words in a free body diagram. This applied horizontal force of 231 newtons. We've got the gravitational force, the weight of the mass acting straight down, and then there's the cable, the tension in the cable acting upwards. If you're not sure what the direction in the tension in a cable is, you simply cut the cable, and if I cut that cable there, then the mass would fall down, so the action of that cable is to act upwards. Okay, so that's the free body diagram. Remember to use words and arrows for your forces. The second question asks whether the mass is in equilibrium, whether the forces acting on the mass are in equilibrium. And the answer there would be yes. And then you need to explain, and your explanation would be to say that the object is at rest and remains at rest. And if that's the case, then the net force acting on it is 0, which means that the forces are in equilibrium. The third part asks you to find the tension in that string, and we're going to use the components method. So this force over here is already in the horizontal plane. We don't need to find its components. That is its component in the horizontal plane. The weight is in the vertical plane, so we don't have to do anything with that. But it's this tension force that isn't acting in either of these planes yet. We need to resolve it. We need to find its vertical component and drop a perpendicular down and find its horizontal component. So we need to resolve this tension force into its two components, one in the vertical plane, one in the horizontal plane, and then we can solve the problem. Well, once we've established what that horizontal component is, then it should be equal to this horizontal applied force. So in the horizontal plane, we know the net force is 0 because the object is at rest all the time. Well, if the net force is 0, then Tx the horizontal component must be exactly equal to the other horizontal force in the horizontal plane. So that makes that very easy. Tx comes out to be 231 newtons to the left. So we're closer to finding T. We've found its horizontal component. Well, if we know this angle here, 30 degrees, and remember alternate angles could put that angle there at 30 degrees. But if we just worked in this right angle triangle here, it's a right angled triangle. So we can use sine. Sine would be opposite over hypotenuse. So sine of 30 would be Tx divided by T. Sine of 30 is Tx divided by T. And if we rearrange that, we get T equal to Tx over sine 30. But we already know Tx, and we can calculate sine 30. So if we plug that into our calculator, we find that tension force, 462 newtons. So what have we applied? We've taken a force, we've resolved it into its horizontal component. We've said Tx is equal to that because there's no net force in the horizontal plane. We could also say that Ty is equal to Fg because these two forces need to be balanced in order for there to be no net force in the vertical plane. So we could also make a statement that Ty is equal to Fg, and we could solve the problem that way. In the second question that I'd like to cover with a different method, the second question we're going to look at is on page 37 of our notes. It's question 2. So let's go there. Here it is here. We've got a 2 kg mass being hung from a point X. Point X is where all the strings are tied together. So there'll be a tension in that string, there'll be a tension in that string, and a tension in string 1. So all the forces are acting on point X. So we need to identify where all the forces are acting, and in this case they're acting on point X. So if point X is at rest, then the net force acting on it is 0. So, there are 4 questions here. Calculate the weight of the 2 kg mass, that's nice and easy. What's the magnitude of the tension in string 3? Draw a free body diagram for point X, and then end off by calculating tensions T1 and T2. But this time I want you to use the triangle of forces method, and when you finish that, come back to the video and look at your solution. Alright, the first one, 2.1, was pretty easy. We needed to find the weight of the 2 kg block. So that's mass times G, and that gave us 19.6 newtons downwards. The second question asks for the tension in string 3. Well, if we look at the forces acting on the 2 kg, we've got a gravitational force and a tension acting up. Because that 2 kg mass is at rest, these two forces are balanced. So the net force is 0, and therefore we can say that T3 is 19.6 newtons acting up there. But the tension in the string is the same throughout, so it acts away from point X, T3. So T3 acts downwards from point X, but it acts upwards on the 2 kg. So we found T3 to be 19.6 newtons. 2.3 asks for a free body diagram. And there we are. Vertically down is the weight, or one could call this T3, because we know it to be the same as the weight of the block. We could call that the weight, or T3. T2 acts upwards, because if you cut that string, point X would fall down, so the action of the string is to pull it up. And T1 acts upwards towards the ceiling. So that's your free body diagram. Two 2.4 asks us to determine T1 and T2. So I've drawn the diagram again. I've got T3 acting down, 19.6. We're looking for T2 and we're looking for T1. And I put some angles in here to help us draw our triangular forces. So let's just look at the statement of the triangular forces law first. Try and find that. There it is. And it talks about if three forces are acting on a point, three forces acting at a point are in equilibrium. So the net force is 0. They can be represented in magnitude, size, and direction by the sides of a triangle taken in any order. So what is that saying? That if we go back to our diagram, we've got three forces acting on a point X, and we know that that point is at rest, so it's not moving, so the net force is 0. So these three forces are in equilibrium. And it says in the law there that we can represent these three forces as the three sides of a triangle taken in any order. So when I apply this law, I like to draw the vertical forces first. So the only force in the vertical plane is T3. So I draw that down my page, label it as T3. We know its value. And then I can take any of these other two forces. So I choose to take T2 first. But when I draw it, I must make sure that I keep its direction constant. So I put my ruler there and I just slide it down the page to the head of T3, and I draw in a vector. I don't know how long to draw it. I'm not too interested in how long it is. This is not a scale diagram. So I'm going to label that T2, and I don't know its value. But I do know the angle that it acts at relative to this one. So that's why I like to draw a vertical line through the point where all the forces act. And I can see now that this is the angle in question in my diagram. Here it is down here. It's between the vertical and T2. And if you look at this right angle triangle, that would have to be 30 degrees. So there's the angle. So a vertical line through the point where all the forces act is very helpful in determining the angle between that, any vertical forces and any forces that other than that. Okay, so we haven't got a triangle yet because we haven't used the third force. So you'll notice I'm drawing my forces head to tail. It's actually just the head to tail method. So my third force, T1, must come down parallel and close the triangle. T1. This diagram is not to scale. I'm simply drawing, I'm trying to keep the directions constant, and I'm just labeling what I have in terms of angles and magnitudes. Let's consider a different order. And as I say, I always like to start with the vertical force. So let's not change that. There's T3. Straight down your page. And then I'm going to take T1 instead. So I'm going to take my force T1, slide it down the page, not changing its direction, and draw it in. I'm still going head to tail. Let's label it T1. And then the third force, T2, should close the triangle. So we've got our three forces drawn as the three sides of a closed triangle. And we've shown two examples of taking them in a different order. But bearing in mind, let's rather work with the vertical force first. That gives us a reference line to draw any angles from. So there's another option that a student could offer as an answer. Right, so let's go back to this one. We've already determined that this is 30 degrees from our original diagram. What about this angle? So this is where that vertical line is so important. So if I draw another vertical line through T1, that's the vertical plane. And then I can see it's the angle between T1 and the vertical. This angle is the angle between T1 and the vertical. And that's 60 degrees. Because the ceiling was horizontal, that was 30. So the vertical must make an angle of 60 degrees with T1. So that gives us 60 degrees, and then we know by the angles of a triangle that this is a right angle, because they've got to add up to 180. So the toughest part of drawing the triangle of forces is really just filling in the angles. But as I said to you, if you draw some vertical lines through the point where all the forces are acting, and maybe another point, or even this point, you can start to determine what the angles are. So if I was working in this diagram over here, I need this angle, and if I go to my diagram, if I've drawn a vertical line through that point, then I can see that this is 30 degrees. So that gives me this angle between T2 and the vertical 30 degrees. I can then look for this angle. It's the angle between the vertical and T1. And there it is, the angle between the vertical and T1, which has to be 60 degrees. Okay, so once you've drawn your triangle, then it's an easy solution. We're looking for T1 and we're looking for T2, and we've got this right angle triangle. So we can use trig ratios. Sine of 30 would be opposite over hypotenuse. Opposite is T1. Hypotenuse is the longest side, it's always opposite the right angle. and that's 19.6. And then we can get T1. And if we put that into our calculator, .6 times sine of 30, that gives us an answer of 9.8 newtons. So we found T1. To find T2, we could just use another trig ratio. In fact, we could just use cos of 30, because the adjacent side to the 30-degree angle is T2. So cos is adjacent over hypotenuse. T2 over hypotenuse is 19.6. And if you solve for T2, we get 16.97 newtons. So we've used the triangle of forces method to solve for the two unknown forces. We had to draw the forces head to tail in any order. So here we go, head to tail, head to tail, and we close our triangle. We close the triangle because the net force is 0 on point X. If the net force wasn't 0, then that third force wouldn't end up closing the triangle, but it would end up somewhere else, and we'd have a resultant force. So try the exercises in the notes and practice these triangles of forces. They can save you time in the exam, but you should know both methods. You should know the components method, and you should know the triangle of forces method. And you should be able to solve any question in the exam.